Matrix operation are the operations that are used to combine various matrices to form a single matrix. The operations such as addition, subtraction, and multiplication are easily performed on the matrix. These matrix operations are very useful to solve matrix problems and to find the transpose and the inverse of the matrix. Various matrix operations that are used to solve matrix problems are the first one is addition of matrix, the second one are subtraction of matrix, the third one is scalar multiplication of matrix, and the fourth one is multiplication of matrix. The first one are addition of matrices. As we add two numbers, we can easily add two matrices. The only thing we have to note is that the order of both the matrices that are to be added must be the same. That is, to add two matrices, we have to make sure that they are of the same order and each element of the first matrix adds with each element of the second matrix to get a single matrix, and thus the addition operation gets completed. As you guys can see, for a matrix A, B, C, D, and matrix B is P, Q, R, S. The sum of the matrix A and matrix B is C. Matrix then C equals A plus B. So A plus P, B plus Q, C plus R, and D plus S. For the example, take three matrices A, B, and C of order 2 multiply 2, 2 multiply 2, and 3 multiply 3, respectively. And the exercise is find the sum of A plus B and A plus C. The A is 2, 9, 5, 6. The B is 1, 7, 2, 3. The C is 5, 4, 8, 2, 3, 7. The solution is matrix A and matrix B can be easily added as their order is the same. The addition of matrix A and matrix B is found as P, or 2 plus 1, 9 plus 7, 5 plus 2, 6 plus 3. And the answer is P, 3, 16, 7, 9. So the matrix A and matrix C cannot be added as their order because they are different order. Next. Here we have properties of matrix addition. There are various properties associated with matrix addition that are for matrices A, B, and C of the same order. Then the first one, there is commutative law. There's A plus B equals B plus A. The second one is associative law, or A plus B plus C equals A plus B plus C. The third one is identity of matrix. A plus O equals O plus A equals A, where O is a zero matrix, which is the additive identity of matrix. And the last one is additive inverse, or it's A plus negative A equals O equals negative A plus A, where negative A is obtained by changing the sign of every element of A, which is the additive inverse of the matrix. The next one is subtraction of matrices. As we add two matrices, can also easily subtract two matrices. The only thing we have to note is that the order of both the matrices that are to be subtracted must be the same. That is, to subtract two matrices, we have to make sure that they are of the same order. Then each element of the first matrix is subtracted with each element of the second matrix to get a single matrix, and thus the subtraction operation gets completed. For example, in here the same. The first one is for any matrix A, B, C, D, and matrix B. PQRS. The difference of the matrix A and matrix B is C. Matrix then C equals A minus B equals A minus B minus Q, C minus R, and D minus S. For the example, for matrices A and B, subtracted the matrix B from matrix A. The A is 2956 and the B is 1723. The solution is matrix A and matrix B can be easily subtracted as their order is the same. The subtraction of matrix A and matrix B is found as, and the A minus B is P. So the 2 minus 1, 9 minus 7, 5 minus 2, and 6 minus 3. The answer is P1233. The next one is scalar multiplication of matrices. For any matrix A, Ig, M multiple N, if we multiply the matrix A with any scalars, or say it K, then the scalar is multiplied by each element of the matrix, and this is called the scalar multiplication of matrices. For any matrix A, B, C, D, if it is multiplied by any scalar K, then K is multiplied A. So K multiplied A, K multiplied B, K multiplied C, K multiplied D. So the properties of scalar multiplication for any matrices A and B of the same order, and lambda and mu are any two scalars. Then the first one is lambda multiplied A plus B. So the lambda is multiplied A plus lambda multiplied B. The second one is lambda plus mu multiplied A. So equals lambda multiplied A plus mu multiplied A. The third one is lambda mu A equals lambda mu A equals mu lambda A. And the last one is negative lambda A equals negative lambda A equals lambda negative A. The second one is multiplication of matrix. Matrix multiplication is the operation that helps us to multiply two matrices. This is different from the algebraic multiplication, and not all the matrices can be multiplied. Only those matrices can be multiplied where the number of the columns in the first is equal to the number of rows in the second. For others, for matrix A, n multiply n, and matrix B, n multiply B, and the multiplication is possible for any other matrices where the column of the first matrix is not equal to the row in the second matrix. The multiplication is not possible. Also, the multiplication of the matrices is not commutative. In others, if matrix A and matrix B are taken, then A multiply B is not equal B multiply A. And here there is transpose operation of a matrix. Transpose operation of a matrix is used to find the transpose of any matrix. Transpose of any matrix is a matrix in which the rows of the matrix are changed to the column of the matrix, and the column of the matrix is changed to rows of the matrix. Suppose we have a matrix A of order m multiply n such that A equals Ig m multiply n, then the transpose of matrix A is represented as A to the power of t, and its value is A to the power of t equals Ig n multiply m. In here, we have inverse operation of a matrix. For any matrix A, its inverse is found only on when A is a square matrix and its determinant is equals to 1. In other words, A equals Ign multiply n. A equals 1. Now, the inverse of a matrix A is a matrix that on multiplying with the matrix A results in the identity matrix. It is represented as A to the power of -1, and the inverse operation of the matrix is an operation that helps us to find the inverse of the matrix. For any square matrix A, we know that A multiply A to the power of -1 equals I, where I is identity matrix of the same order as A. In here we have problems example. Find the value of A, B, C, and D. If A minus B, 2A plus C, 2A minus B, and 3C plus D equals -1, 5, 0, 13. So the solution is that we know that given A minus B is -1. That is the first one. And the second one, we know that 2A plus C are 5. The third one, we know that 2A minus B are 0. And the fourth one, we know that 3C plus D are 13. So we have A equals 1. Putting the value of A in equation 1, we get B equals 2. Putting the value of in equation, the second, 2 plus C equals 5, so we get C is 3. Putting the value of C in equation 4, we find 9 plus x, uh, 9 plus x equals 13, so D is 4. So, in conclusion, A is 1, B is 2, C is 3, C is 3, and D is 4.
Okay, the next one is determinant of a matrix. Determinant of a matrix is a number associated with that square matrix. The determinant of a matrix can only be calculated for a square matrix. The determinant of a matrix is calculated by adding the product of the elements of a matrix with their cofactors. Here is determinant of 2 times 2 matrix. The determinant of any 2 times 2 square matrix A equals ABCD is calculated using the formula determinant A equals BC is subtracted from AD. For the example, find the determinant of A equals 3, 2, 2, 3. Determinant of A is calculated as determinant A equals to the product of 2 times 2 is subtracted from the product of 3 times 3 equals 4 is subtracted from 9 equals 5. Determinant of 3 times 3 matrix. We use the cofactor methods. Minors of a matrix are the determinants of the smaller matrices that are left after removing one row and one column from the original matrix, and the cofactor of an element is calculated by multiplying the minor by -1 to the power I added to j, which accounts for the position of the element within the matrix. So here, matrix A equals A, B, C, D, E, F, G, H, A, and the determinant is A from here, and we're removing one row from the A, so we get the E, F, H, A. From the previous slide, it is we use determinant, so E, A, negative F, H, and we do the same for the all rest. For the example, evaluate the determinant A 1 through 130410201. We see the third column here has most number of zeros, so it will be easier to expand along that column. So determinant A equals -1 to the power 1 added to 3 multiplied by 0 and multiplied by the smaller matrix here. We remove here and we got 1 to 0 added to -1 to the power 2 added 3 multiplied by 0, and the smaller matrix is 1, 3, and 2, 1. 1, 3, and 2, 0 added to -1 to the power of 1 added to 3 multiplied by 1, and the smaller matrix is the last smaller matrix is 1, 3, 4, 1, and determinant of matrix A equals -11.
Okay, next in here, adjoint and inverse of a matrix. First, adjoint of a matrix. The adjoint of a matrix, also called the adjugate of a matrix, is defined as the transpose of the cofactor matrix of that particular matrix. For a matrix A, the adjoint is denoted as adjoint A. On the other hand, the inverse of a matrix A is that matrix which, when multiplied by matrix A, gives an identity matrix. The inverse of a matrix A is denoted by A inverse. So we have to adjoint of 2 times 2 matrix. While if A, B, C, D, then D mean B mean C, A as a adjoint of A. Next. Then adjoint of 3 times 3 matrix. Let the determinant of a square matrix A be determinant A. If A1, 1, while A row 1 and column 1. A1, 2, A1, 3, A2, 1, A2, 2, A2, 3, A3, 1, A3, 2, A3, 3. Then determinant A is A1, 1 until A3, 3. The matrix formed by the cofactor of the elements is A1, 1, A1, 2, A1, 3, so on until A3, 3, where A1, 1 is -1, the square of 1, the power of 1 added 1 multiplied by A22, A23, A32, and A33, and the equal of A22, A33 minus A23 multiplied A32. Then A12 equal is -1, the power of 1 added 2, and that's the multiplied by A21, A22, A31, A33. Then the equal is minus A21 multiplied A33 plus A23 multiplied A31. Okay. So A13 equal -1, the power 1 added 3 multiplied A21, A22, A31, A32 is A21 multiplied A32 minus A22 multiplied A31, so on until A33. Next. Then the transpose of the matrix of cofactor is called the adjoint of matrix A and is written as adjoint A. Let A be a square matrix. Then adjoint A multiplied A is A multiplied adjoint A is determinant A multiplied I. And adjoint A is A11, A21, A31, so on until A33. The product of a matrix A and its adjoint is equal to the unit matrix multiplied by the determinant A. Let A be a square matrix, then adjoint A multiplied A is A multiplied adjoint A is determinant A multiplied I. Let A is A11, A12, A13, A21, A22, A23, A31, A32, A33, and adjoint A11, A21, A31, A12, A22, A33, A13, A23, A33, A multiplied adjoint A is A multiplied adjoint A is next A11, A12, A13 until so on. A33 multiplied A11, A21, A33, so on A33. And the equal is determinant A 0, 0, 0, determinant A 0, 0, determinant A, and the equal is determinant A multiplied I. Okay. The second one is inverse of a matrix. If A and B are two square matrices of the same order, such that AB is BA is I, while I is unit matrix, then B is called the inverse of A, i.e. B is A inverse, and A is the inverse of B. Condition for a square matrix A to process an inverse is that the matrix A is non-singular. While A not equal 0 if A is a square matrix and B is the inverse, then AB is I. Taking the determinant of both sides, determinant AB is determinant I, or determinant A multiplied by determinant B is I. From this relation, is it clear that determinant A not equal 0, the matrix A is non-singular. A multiplied by A inverse is I. So A inverse is 1 divided by determinant A, then multiplied by adjoint A. Then we have to problems example. Find the inverse of a matrix A while A 4, 9, 3, 7. The answer is A inverse is 1 divided by AD minus BC, then multiplied by D minus B minus C, while D minus B minus C, A is adjoint A. Then A inverse is 7 minus 9 minus 3 and 4.
Okay, the last subtopic is solving linear equation using matrices. First one is augmented matrix. A matrix formed by combining columns of two matrices is called augmented matrix. An augmented matrix is used to perform elementary operations, solve a linear equation, and find the inverse of a matrix. Let us understand through an example. Okay, first we see the right side here. Matrix A equals A, B, C, D, E, F, G, H, A. Matrix B equals P, Q, R. Augmented matrix AB. So the augmented matrix is like this. Okay. Let's say we have a matrix A equals A1, B1, C1, A2, B2, C2, A3, B3, C3, X equals XYZ, B equals P1, P2, P3. Then augmented matrix is formed between A and B. The augmented matrix for A and B is given as A augmented matrix B equals A1, B1, C1, A2, B2, C2, A3, B3, C3, P1, P2, P3. Matrices are used to solve linear equations. To solve linear equations, we need to make three matrices. The first matrix is coefficient, the second matrix is variables, and the third matrix is constant. So for the example here, let's say we have two equations given as a1x plus b1y equals c1 and a2x plus b2y equals c2. In this case, we will form the first matrix of coefficient. Let's say a like this, and the variable like this, and the coefficient like this. So then the matrix equation is given as ax equals b.
Before the exercise, we have some our references. Please show the references slide.
Maybe before we are going to the exercise, you can ask your friend first. Is the topic is clear enough for them, or maybe your friends have any question about this topic?
Okay. Does anyone have any question about matrix material?
Class, do you have any question for this group? Or maybe is it clear enough for you? Please tell us.
I think that's enough, ma'am.
Okay. Someone say that it is clear enough. The others? Okay. If there is no question, please continue this discussion, yeah? The group have 3 exercises. Number 1, it is about determinant of a metric. Number 2, about the inverse. And number 3, you have to find the value of x and y. I think it is not so difficult, yeah, for you. So please please try to answer this all question, and you can try to explain it to your friend. Anybody wants to answer number 1, maybe? Okay, you can see on our group, Nirmala wants to answer number 1. Okay, Nirmala, please, the time is yours.
Yes, ma'am. Thank you. Wait a minute. Is it see on your screen, mom and class?
Yeah.
Okay, thank you for the time. On the first problem, we have to find the determinant from metric A, and metric A is contained with 2, 3, 1, 6, 5, 2, 1, 4, 7. And I'm using cofactor method to solve this problem. So here we have 2 multiplied by 5 multiplied 7 minus 4 multiplied 2 subtracted by 3 multiplied 6 multiplied 7 minus 2 multiplied 1 added to 1 multiplied 6 multiplied 4 minus 5 multiplied 1. So we here have 2 multiplied 27 subtracted 3 multiplied 40 added 1 multiplied 19. And the result is 54 subtracted by 120 added 19 is equal to minus 47. Is my answer correct?
How about Nirmal answer the group?
Yes, the answer is correct.
All right, thank you.
Okay, thank you, Nirmala. So the question number 2. Number 2, please. About the inverse of matrix.
So the question is find x and then y. That the equation is 2x plus 3y is equal to matrix 2, 3, 4, 0, and then 3x plus 2y is equal to matrix 2, negative 2, negative 1, 5. And then I'm met the equation for this matrix to be 2x plus 3y is equal to matrix 3, 2, 3, 4, 0 is equation 1, and then 3x plus 2y is equal to matrix 2, negative 2, negative 1, 5 is equation 2, and then the first equation I multiplied by 3, then the product is 6x plus 9y is equal to matrix 6, 9, 12, 0. And then I made this one as equation 3. And then the second equation, I multiplied by 2. And the product is 6x plus 4y is equal to matrix 4, negative 4, and negative 2, and then 10. And for this one, I made as equation 4. And for the next, I subtract equation 4 from equation 3 because of 6x and then negative 6s. 6x is x house. And then the value is negative 5y is equal a matrix negative 2, negative 13, negative 14, and then 10. And for got a value of y, we multiplied all of segment with negative 1 over 5, then the value of y is equal to matrix 2 over 5, 13 over 5, 14 over 5, and then negative 2. And for got a value of x, I substitute y to first equation, and then I got 2x plus 6 over 5. 39 over 5, 42 over 5, and then negative 6 is equal to matrix 2, 3, 4, 0. And then I subtracted all of segment with this one matrix, and then for for this segment, this one zero matrix, and then we know that the value of zero matrix is 0. Then the segment is 2x is equal to matrix 2, 3, 4, 0 is subtracted to matrix 6 over 5, 39 over 5, 42 over 5, negative 6. And then 2x is equal to matrix 4 over 5, negative 20 over negative 24 over 5, negative 22 over 5, and then 6. And then for all segment, we multiplied by 1 over 2, and we got the value of x is 4 over 10, negative 24 over 10, negative 22 over 10, and then 3. And we made a simple matrix, and we got the value of x is 2 over 5, negative 12 over 5, negative 11 over 5, and then 3. Is my answer is correct?
Yes, they all are correct.
Okay, thank you, Nurhaliza. And we have the last question about the inverse of matrix. Anybody? For number 2, the question number 2.